Okay. Mm, so last time we proved this famous Castelnuovo-Severi inequality for well, for some numerical characteristics of line bundles on curves, and I mean on products of curves on decomposable surfaces. And today we will consider arbitrary surfaces indecomposable. So X will be a projective smooth, irreducible surface, two-dimensional variety, and we will have line bundles and we will define certain bilinear pairing like this, well, a close relative of the pairing like this, defined in case our surface was decomposable. Okay, but if you remember this definition, it really used the decomposable structure of our surface. So we do need some other ideas. And let me first motivate this new definition, and then I will give. Well, in fact, okay, let me give this new definition and then and then motivate it. So this is the Euler characteristic of the underlying surface minus the Euler characteristic of L inverse minus Euler characteristic of M inverse plus the Euler characteristic of their product. Okay, so well, it looks somewhat similar to our well, how to say, Langle pairing, and in the exercises I will send out today, you will have the exact relation, but first let me somehow motivate this new pairing. So we will consider L equals OX of C for some smooth curve, and M equals OX of D. So here C and D are smooth curves, that is effective divisors. On X. Okay, and now we are going to count the intersection points of those two. So our goal is to count this, but again, as always, those intersections might not be transversal, so we have to assign to each intersection point some multiplicity. And we already did this, say for P2, yeah, when we discussed Bézout theorem. And in a sense, this is so what we're doing now is sort of Bézout theorem, but for arbitrary surface, not necessarily for P2 for projective plane, but for our surface X. So the multiplicity at a point P of the intersection is defined as a dimension of the local ring at this point over the sum of two ideals Okay, so this is literally the same definition as we had for projective plane, for two curves on projective plane. Okay, and then we define the total intersection as the sum over all points of local intersections, multiplicity. Okay, and this is what we want to compute. So well, to compute this, in terms of Euler.
Количество точек пересечения должно быть конечным.
Oh yes, certainly, because maybe I should say that they're smooth and how to say, distinct, well, but different curves. So they don't have common irreducible components. That's what I mean. But then their intersection necessarily has dimension 0, and well, any variety of dimension 0 is finite, right? Finitely many points, because we're in algebraic geometry, not in analytic. Okay, so we want to compute this in terms of Euler characteristics, and then we consider the standard resolution.
Из чего следует, что нет неприводимых компонентов общих?
Well, we assume this. So no common irreducible components.
Спасибо.
Okay, so resolution we used for Bezout theorem on projective plane is 0 goes to the invertible sheaf like this, then goes to the direct sum of two invertible sheaves, and then goes to the structure sheaf, and then goes to...
Извините, а как ко всему этому относится многообразие X? Внутри X этого существуют эти кривые.
Yes, we have our smooth projective surface X, and in this surface, inside this surface, we have two smooth curves. But not
вижу, увидел. Все,
yeah.
Спасибо.
But these curves are not necessarily irreducible. Yeah, they may have various irreducible or the same connected components. Okay, so then we're interested in the so this last rightmost sheaf is just a skyscraper sheaf. I mean, its support is 0-dimensional, and so dimension of global sections of O intersection C and D is the same as the Euler characteristic of this sheaf. Okay, and this Euler characteristic can be computed from this exact sequence. So we get that this is chi of OX minus chi of OX minus C minus chi of OX minus D plus chi of OX of minus C minus D. Okay, and then we see that this is exactly the pairing of L and M, where L is OX of C and M is OX of D. Okay, you see the definition of the pairing in the upper part of the page.
But
okay, so
why
this, yeah.
Why
Yeah.
is the dimension of global sections of OC intersected with D is
Yeah.
Is
The Euler
characteristic?
Because this sheaf is supported at zero-dimensional varieties, C intersection D. It's not, sorry, it's not quite a variety. I mean, if there are tangent points, then this C intersection D acquires nilpotent elements at these points. So it's not quite a variety, it's a scheme. We'll discuss this in an hour. But anyway, whatever is this structure sheaf of C intersect D, it has zero-dimensional support, and hence it does not have higher cohomology. It's direct sum of skyscraper sheaves. So
by
no
theorem of
and
Grothendieck.
then, yeah, and then well, the characteristic is just given by the dimension of global sections of H0, no H1, no H2, so on. Okay, so this was some motivation once again, and now we will study this pairing and prove a few important theorems about it, and then in the home assignment you will prove the very important Hodge index theorem, that this pairing is almost negative definite. I mean, if you fix some very ample line bundle, your surface is projective, so it carries a very ample line bundle, and the self-pairing of this very ample line bundle is certainly positive. But if you consider the orthogonal complement of this very ample line bundle, then on this orthogonal complement, that is sort of codimension 1 subspace of Picard, the pairing is negative. And this is the very important and famous Hodge index theorem that you will have in the home assignment. Today, we're going to prove the Riemann-Roch theorem for line bundles on surfaces, which is very important also. And to do this, first we have to check that this pairing is really pairing. I mean, it's bilinear pairing. And to do this, we start with a lemma that we proved last time, but it's a variation of the last time lemma. So for any invertible sheaf, we can find
Сейчас нам не нужна приведенная группа Пикара.
No, you see, we defined the reduced Picard group for decomposable surface, right? Because when we had projections to two factors, to two curves, then we could pull back line bundles from these curves, and then we can define the reduced Picard group as the quotient model of these pullbacks. And now our surface is general. There are no projections to curves. There's nothing to pull back. Okay.
Спасибо.
So there are disjoint, smooth curves E1 and so on, EC in X, and disjoint smooth curves D1 and so on, DD in our surface, such that our line bundle is OX of the sum of C curves minus the sum of D curves. So C's and D's may intersect. There are no intersections between various C's and between various D's, but C's and D's can possibly intersect. Okay, and the proof is by Bertini theorem. So we find a very ample invertible sheaf M on X, such that the tensor product M and L is also very ample. Okay, so it means that for general sections.
Там, наверное, L в какой-то степени, существует такая степень у L, или мы просто...
No. You vary, L is fixed. You vary M. Yes, and you find it very, very ample. So first of all, it is M very ample by itself, but also M tensor L is also very ample. Okay,
Да, спасибо.
that's possible. So for general sections like sigma in M and like tau in global sections of M tensor L, their zeros are smooth, namely the zero divisor of M. Sorry, zero divisor of sigma is the union of DJs, and the zero divisor of tau is the union of CIs. Sorry. And that's it. Okay, so this lemma is proved, and it will allow us to compute this pairing, just similar to what we did last time. So no new ideas are required. Pardon me?
Once again, could you please repeat why are they disjoint?
Because by Bertini theorem, the hyperplane a general hyperplane section is smooth.
I
so
see,
it is
yeah,
a disjoint union of smooth,
uh-huh.
irreducible connected components.
Okay, yeah, thank you.
And very nice birds are singing around you, so you may not mute yourself. You better switch your mic, yeah, on. Right, great, thanks. And can you see these birds or only hear?
Actually, it's difficult to see them. They are inside some tree. I cannot see through trees. Yeah.
Great, but still I envy you very much. Thanks. So now the next computational lemma is that this pairing. I mean, we have two. Sorry. Maybe I shouldn't have called this very ample guy by M, because now M is arbitrary. Okay, so I will write this down. This is the sum of degrees of M restricted to those curves Ci's minus the sum of degrees of M restricted to dj's. So for any M invertible sheaf on X, and L is OX of some Ci's minus some dj's as above. Okay, so I do not require this M to be very ample as in the previous lemma. Sorry, isn't the proof of previous lemma. Okay, and hence this pairing is linear in M, and by symmetry, this pairing is also linear in L. Okay, so it is a bilinear pairing indeed. Okay, so let's prove it. So as I said, the proof is the same as the one of the previous similar statement from the previous time, and there are no new ideas. So we use two exact sequences. L goes to OX of C. The C is the union of CI's. Goes to the sum over J of OX of C restricted to dj's. And also 0 goes to L inverse OX of D goes to the sum over I's OX of D restricted to CI. Okay, just well, they're very similar. One for L, another for L inverse. And then we can compute the Euler characteristics. And let me write this down on the next page.
Can I ask about the previous lemma? Why?
Okay, let's go back.
Why why we can find Ci and Di such that this OX is the L we started with? We started with L fixed.
Yes. Well, I just you use the only fact that L is the ratio of two line bundles, M tensor L and M, right? So M is O of D, and M tensor L is O of C. Right?
Yes.
Okay.
Okay.
Yeah, so let's have one more look at those two exact sequences and write down the Euler characteristics. We get chi of OX of D minus the sum of Euler characteristics over OX of D restricted to Ci's. And now let's twist it by M inverse, and we get the chi of L inverse tensor M inverse is chi of M inverse of D minus the sum of characteristics of M inverse of D restricted to Ci's. Okay, and now we compute this pairing of L and M, and just by definition, this is the Euler characteristic of the ambient surface minus the Euler characteristic of L inverse minus the Euler characteristic of M inverse plus the Euler characteristic of their tensor product. Okay, and now we just plug in the above expressions for Euler characteristics. So we get the Euler characteristic of the ambient surface minus the Euler characteristic of well, just so I want to write down the Euler characteristic of OX of D. Yeah, from the very first formula, but I write it in some strange way that will well make apparent its later use. So I write OX of minus D, but inverse. It's just OX of D. Now minus chi of M inverse plus again I write this in some strange form, chi of M of minus D inverse, and also plus the sum of Euler characteristics of O of D restricted to CIs minus the sum of Euler characteristics of M inverse of D also restricted to CI. Okay, and now the second line is just the sum of degrees of M restricted to CIs.
Почему это?
Because well, I think we discussed this with you last time, Sergey. Because we are discussing certain line bundles on the curves CIs, namely the line bundle O of D and M inverse of D, right? And then the difference of two such Euler characteristics is the Euler characteristic of M. Yeah. Well, let me write it down here. Chi of O minus chi of M is negative degree of M for any line bundle, well, invertible sheaf M on a curve CI, right? That's what we use. Yeah.
Спасибо.
But let me now erase this. Okay, so this equality we just discussed was for the second line, but the first line was arranged specifically so that it is apparently the pairing of OX of negative D and M. Okay. Fine. So we have to compute this pairing. To compute the pairing OX of negative D and M, we use the exact sequences OX goes to OX of D, goes to OX of D restricted to D, and also its twist. M inverse goes to M inverse of D, goes to M inverse of D restricted to D. And from this, we see that the desired pairing, x of minus D with M, is the Euler characteristic of OX minus the Euler characteristic of M inverse. Well, let me go to the next line. Plus the Euler characteristic of M inverse plus the Euler characteristic of M inverse of DI restricted to DI, or maybe J, I should say J. And also minus the characteristic of OX minus the sum of Euler characteristics of OX of DJ restricted to DJ.
Куда пропала Эйлерова характеристика от OX минус D? Куда пропала Эйлерова характеристика от OX минус D? Нужно ее еще вычесть.
So that's what we do. The Euler characteristic of OX of D, this last line, for example, yeah, with the two differences in the last line, they come from the first exact sequence. Yeah, the Euler characteristic of OX of D is the sum of Euler characteristic of OX and OX of D restricted to D, right? Now the middle line comes from the second exact sequence, right?
А вот тензорное произведение во что превратилось?
It is M inverse of D. Yeah, the tensor product of when I have two line bundles, we need the Euler characteristic of their inverses tensor product, right?
Да.
And this will be OX of D tensor M inverse. So it's M inverse of D, and we compute its Euler characteristic from the second exact sequence. Okay, so we get those things.
А откуда тогда возникла вторая сумма по ограничению вот этому, ну, во второй строчке сумма?
But it's just
из второй точной последовательности.
Yeah.
Все, спасибо.
Okay, fine. And now here many things cancel out, like chi of x plus, and here minus, chi of M inverse minus, then plus, and so on. And the only thing that remains is, just as we argued before, negative sum over J, the degrees of M restricted to dg. So the desired equality is proved. We wanted to prove here, yeah, that the pairing of L and M is the sum of degrees of M restricted to the positive divisors minus the sum restricted to the negative divisors. And that's what we did. Fine. So this is a useful formula that we'll use in a moment. But also, this proved that our pairing is bilinear. So it's really a pairing in the usual sense. Okay. So now we can formulate and prove the Riemann-Roch theorem. For invertible sheaves. On surfaces. So it's not the full strength, full generality Riemann-Roch, because I guess you've heard something about Riemann-Roch theorem, and you need characteristic classes. Yeah. So the idea is that something algebraic geometric, like Euler characteristic or vector bundle, is computed in some purely topological terms. And these topological terms, they include characteristic like Chern classes of this vector bundle. But when we deal with line bundles, you only have the first Chern class, and the second Chern class vanishes. Okay, so from this point of view, this Eisenhower theorem is not most general. It only works for invertible hues for line bundle. So it says that the Euler characteristic of a line bundle is 1/2 the pairing of L with L twisted by the opposite canonical class plus the Euler characteristic of the structure sheaf, or else we can rewrite it as a negative 1/2 of pairing of L with its third dual bundle, OX tensor L inverse, plus the same Euler characteristic of our surface. Okay, and you see that how to say, roughly this Euler characteristic is quadratic in L. Yeah, because it involves some pairing, well, plus some linear term, plus some constant term, but it's quadratic. And for curves, the Euler characteristic was linear plus some constant term. Yeah. So, oops, sorry. Okay. For curves, we had just linear term, degree of L plus some constant, 1 minus G. Right. So, and it's some general phenomenon. I mean, if we consider, say, line bundles on 3-dimensional variety, then its Euler characteristic will be given by some cubic formula, and so on. But unfortunately, we will not go into Riemann-Roch theorem. We will do something else. Though it is a very deep and general subject and useful. But we will just, this is the last thing we will do about Riemann-Roch theorem. Okay. So let's
and once again, yes. where is the statement? So the statement is that the first equality holds, yes? And the second is
yes. It's a computation of Euler characteristic of a line bundle on a surface, on a smooth projective surface.
Okay, and
yes.
Yeah, but we can expand this bilinear pairing in by definition, and what will we obtain? Okay, continue.
Thanks. So, well, again, we write L as OX of sum of CI's minus the sum of DJ's. And again, we consider exact sequences. L goes to OX of sum of CI's, goes to direct sum of OX of the sum of CI's restricted to DJ's. Okay, and another one goes to OX of CI's then goes to direct sum over i's of OX of maybe let me write over k's. Here it's sum of ci's, but then I restrict to ck's. This and from this, the Euler characteristic of L that we are after is the Euler characteristic of OX plus the sum of, or maybe, okay, the sum of all characteristics of OX of the sum of the i's restricted to the k's minus the sum of all characteristics of OX the sum of ci's restricted to dj's okay, and now we rewrite it in the following way. Well, how do we do this? Maybe I write chi of OX, and then I have plus the following two terms: the sum of over k, all characteristics of O ck's plus the sum of degrees of O x of the sum of ci's restricted to ck's. And Sergey, we just discussed this some 20 minutes ago, didn't we? Right? This is the first sum, and the second sum is we subtract the sum over j all characteristics of O dj's minus the sum of degrees of OX of sum of ci's restricted to dj's. It's over k. Okay, and finally, this is equal to the Euler characteristic of OX plus the pairing of OX twisted by ci's with L plus sum over k characteristics of the curves ck minus the sum over j characteristics of dj. Okay, so now we have this sum of four terms, and we have to recombine it somehow. Well, maybe let me copy this on the next page. Sorry about this. I will just copy this on the next page. Okay, and this was equal to the desired Euler characteristic of L, and maybe also let me copy here the statement of the theorem. So we want to prove that chi of L, and we know that chi of L is equal to this sum of 4 terms, that it is equal to chi of OX. That's good. That's the first term. Plus minus plus 1/2 the pairing of L with itself tensor the negative canonical class. So we want this, and to this end we need the following equality, that the last 2 terms chi of O ck minus the sum of all characteristics of O dj equals minus 1/2 of the pairing of the canonical class with L, and minus 1/2 the pairing of OX of sum of C k's. So yeah, with L, minus 1/2 of the pairing X of sum of dj's with L. Okay, and it remains to prove this.
Извините, не совсем понятно.
Yes.
Мы хотим доказать, что у нас будет возникать вот в эйлеровой характеристике L, вот L, запятая L, тензор омега x минус 1. А здесь у нас присутствует такое аддитивное слагаемое с омега x. Как оно будет превращаться в мультипликативный множитель в тензорном произведении, если мы даже вот это докажем?
We know that our pairing is bilinear. Yes, so this pairing of L with L tensor omega x inverse is the pairing of L with itself minus the pairing of L with omega x. Yeah, just by bilinearity.
Еще вопрос. Почему L, L равно O от x сумма CI, ckт минус O от x, то есть O от x можно выносить спокойно из этого, из-под суммы.
No, то есть again, by bilinearity. L is O x of some CI's minus some DJ's, and well, it's just the tensor product of the corresponding line bundle. Yes, and you use by bilinearity.
Ну, я имею в виду то, что можно вот эту разность рассмотреть как O от x минус O от x.
L is the sum over I of the pairing with O of CI's minus sum over J, the pairing with O of DJ's. Just by bilinearity. Yeah?
Спасибо.
Okay, so let me erase this. Okay, so we need to prove this last equality, right? And we're almost done because we know that the canonical class of any curve CK is the canonical class of the ambient surface twisted by this divisor. Oh, sorry, Ci maybe to write here. Restricted to Ck. And also we know that the canonical class of D I ran out of indices. Maybe M is the canonical class of the ambient surface of the sum of dj restricted to dm. These are adjunction formulas. Fine. And also we know that for any curve, again, I'm out of letters, C, D, whatever. S, we didn't use S, right? For any curve S, the Euler characteristic of its structure sheaf is 1 minus G, and this is negative 1/2 of the degree of its canonical class. Fine. So when we write, well, we need this equality. Yeah, let me denote it. This equality by star. The left-hand side of this star is the sum of characteristics of our curves minus the sum of characteristics of the polar curves. And we know that this is minus 1/2 sum over k degrees of omega x sum of c i's restricted to ck plus 1/2 of the sum over j degrees of omega x sum of d whatever m's restricted to dj. Okay, but now this you can rewrite back in terms of pairing, and you get just what you need. So this is negative pairing of omega x and L minus the negative pairing of sum of the i's with itself. Well, but I'm somehow out of place now. Okay, let me write over 2 minus the pairing of sum of the j's with itself, and this was pairing over 2. Yeah, and that's it. That's just what we wanted. So this is the right hand side of our equality just by linearity. Okay, and what we use here is that whatever like if you wish right here, if I take negative a minus b minus minus b, a minus b, and this is just b squared minus a squared. I mean, by a I mean this O of sum of CIs, and by b I mean O of sum of DIs. So we proved it. And maybe I erase this.
Can I ask?
Yes.
On again, why the difference of Euler characteristics is the degree of something? You explained it, but I missed the last.
Well, once again, so chi of any line bundle, whatever, n on a curve minus chi of O on this curve is the degree of n. That's what you ask?
Yeah,
Daniel?
what? Why it is so?
Why is it so? Just because, well, you know that.
Riemann-Roch?
Well, for one thing, yes, but somehow Riemann-Roch is deduced from this. So n is OS of sum of some points x I minus sum of yj, and so here I goes from 1 to n, here j goes from 1 to m, and the degree of n is n minus m. That's clear, yeah. But then if you compute Euler characteristic from Schrödinger sequences, you see that each time you add a point, it increases by 1. Each time you subtract a point, it decreases by 1, right? Okay, so
you mean exact sequence, exact triples involving this?
But I think that this is one of the proofs of the Riemann-Roch.
Yeah, right. When you prove Riemann-Roch, you only need to know the Euler characteristic of one single sheaf, for example, structure sheaf or dualizing sheaf, and then you deduce it for arbitrary sheaf just by using this. Okay.
Yes, and on the question on when you when you apply the third duality, this form changes sign, and you.
Which form?
This bilinear form between sheaves which we discussed. You used the properties and that.
Yeah. So we know that the pairing of L inverse and M is negative pairing of L and M. Yeah, it's again by bilinearity.
Okay.
Okay. So now
Можно еще спросить?
Yes, certainly.
Вот на прошлых лекциях мы вводили дефект, мы вводили спаривание треугольное такое.
Right.
Я так понял, мы должны где-то были сегодня его применять. А где мы?
No, because it was only used for the case of decomposable surfaces that were products of two curves. And today it was some generalization for arbitrary surfaces. And in your home assignment for April 12th, I will send it out in half an hour. In the first problem of April 12th, you will have a relation between this angular bracket and this square bracket.
Все-таки можете
Yes.
сказать, где вот мы получили вот то неравенство большое в прошлый раз, получили вот эти утверждения. Где мы воспользовались всем этим машинерией вот этой дефекта?
I don't quite understand. We took some pains to prove this Castelnuovo-Severi inequality last time, but it only worked for decomposable surfaces, right? And essentially, this was the Hodge index theorem. We used some negative definiteness, or maybe positive definiteness of some bilinear form. And in your home assignment of April 12th, you will prove this Hodge index theorem for arbitrary surface, not necessarily decomposable. But its application to curves, say for point counting, that we'll have next time, only uses decomposable surfaces. But the statement itself, this definiteness of some bilinear form, is true for arbitrary surface. In fact, it's true in utmost generality for arbitrary varieties. Only have to formulate it correctly. The Hodge index theorem is very general.
Вот теория об индексе, вот это будет максимальное приложение теории о дефекте.
So last time we proved Hodge index theorem, though we did not call it this way, but we proved Hodge index theorem for decomposable surfaces. And the Hodge index theorem for arbitrary surfaces will be subject of your home assignment for April 12th. Yeah?
Теорема о Ходже, это вы имеете в виду, как считать вот эту скобку? Или
No,
что?
Hodge index theorem. Okay, let me write it down. I mean, it's written in the home assignment, so I didn't want to repeat it here, but let me repeat it. So fix a variable invertible sheaf L on our surface X. Then two things. First, the pairing of L with itself is positive. Second, the pairing on its complement. Well, how should I say this? Maybe, sorry. On the orthogonal complement inside the Picard group of X is negative. Not necessarily negative definite, but negative. So, I mean, M is less than or equal to 0 if the pairing of M and L is 0. Okay. So did I answer your question?
Да, ну эту теорему я помню. А из этого что следует? Ну хорошо, получили мы такую форму, да. Мы на этом и закончили.
X is, yeah, if X is decomposable, then Hodge index implies Castelnuovo-Severi inequality.
Все вот для этого неравенство создавалось. Понял теперь, спасибо.
But for decomposable surfaces, we already proved Castelnuovo-Severi inequality last time unconditionally, without using Hodge index. But it's also it's an equivalent formulation of Hodge index theorem for decomposable surfaces. Okay.
Спасибо.
Fine. So now we are done with the textbook by Kempf, and maybe in the remaining 15 minutes, let me cover the general theory of schemes. And first of all, let's define the non-maximal spectra of rings. So now A is an arbitrary unital commutative finitely generated algebra. For example, it can be oh no, that's not algebra, it's a ring, sorry, that's an important thing. So no ground field anymore. So it can be still the ground field like this, but with nilpotence. Or it could be just integers, or the ground field could be not algebraically closed, like this. So any ring like this, no restrictions whatsoever. So it's a vast generalization of what we had before, and we have to define this spectrum, but not necessarily maximal. So it's bigger. This spectrum of A will contain what we had before, the maximal spectrum of A, namely, well, let me only mention that it was defined, introduced by a student of Emmy Noether, Wolfgang Krull, at the same Krull as Krull dimension, in the middle of 30s, maybe 36, something like this, and as a set, this is just the set of all prime ideals, not necessarily maximal. So, for example, if say A is something like this, then its spectrum will be the set of all points, and these correspond to maximal ideal, right? Generated by T minus A, and there will be one more point. It's called eta. It is the so-called generic point. Okay, and generic in the sense that everything else will lie in its closure. So any A lies in the closure of this point. So what is the Zariski topology is just the same. So the definition of Zariski topology stays the same, intact. So the closed subset are Z of I for any ideal I, and the Z of I is the set of prime ideals. Sorry, such that P contains I. Okay, so this eta, for example, is the corresponds to the zero ideal, right? Yeah, the zero prime ideal. The generic point is the zero ideal. So it's not necessarily prime. Yeah, it's prime only is if A is that does not have zero divisors. Okay, so I defined some set with topology, and now I need to define the structure sheet. And again, it's very similar, but certainly it was not defined by Wolfgang Krull because there were no sheaves before the Second World War, and it was only defined by Pierre Cartier in about 1955, so about 20 years after the definition of spectrum itself. But the definition is just the same somehow, just the same as we had for varieties. Similarly to the case of varieties. But with a single difference. That it cannot be a subsheaf of functions like our topological space to K, since there is no K. Well, it is something in between the classical definition and the definition of discontinuous sections. So if you remember, discontinuous sections took values in the stocks. Yeah, each point went to an element of the corresponding stock, and the same here. So now the sections, the local sections of the structure sheaf are well, such discontinuous sections that the section S of point P lies in the corresponding localization of A at P. So it is S inverse A for S equals A minus P. Like this. Okay, and those sections locally are required to be of the form A over B, where B does not lie in P. Okay, just what we had for the classical case and for maximal spectra. Okay, and then there is an important theorem that the global sections of the structure sheaf. Oh, sorry. Is nothing but the ring A itself, but the proof is just the same. We gave a proof in case of varieties. I mean, in case of rings without nilpotents and their maximal spectra, and the proof is the same here. And more generally, if we consider the standard open subsets, BF or maybe DA, then it will be just the localization A standard open subset. And those form a base of topology. Okay. So finally, the desired definition of schemes. Is glued of spectra. So it is a ringed space locally isomorphic to spectrum of A with the structure sheaf. That's it. And well, the bottom line is well, maybe almost all theorems of Kemp hold true for schemes with well, or more or less the same proofs. And well, we just have 1 minute. Maybe I'll give an example of I'll give a counter example, and then next time we'll consider curves over over finite fields as examples of schemes, and then we'll turn to the existence construction of Hilbert schemes, and there we will use a lot of machinery developed for varieties, but applied to schemes. So just one stupid counterexample. So we proved, Kemp proved, that if all the fibers of a coherent sheaf are of the same dimension, then the sheaf is locally free. Okay, and now let's consider, in place of variety, let's consider X to the spectrum of the ring K of epsilon modulo epsilon squared, and our sheaf F is localization of certain module, and this module is just the augmentation module. Okay, and then there is just one point. You see, still it is just one point. And at this point, the dimension of the fiber of our sheaf is 1, certainly, but there is nothing to compare to. Yeah, so it's constant because it's just a function of 1 point. But clearly, this module is not locally free. Okay, so we will encounter this counterexample in our study of Hilbert schemes, and it will cause certain difficulties, but they will be easily overcome. Next time we'll consider some less pathological examples without nilpotents, but over non-algebraically closed fields. So there are some subtleties also, but we'll discuss them next time. And next time I plan to come to the math department in person. So I hope we will be able to have a YouTube live broadcast. Okay.
I'm sorry, but people usually say that this X is not just a point; it is a point with a tangent vector attached to this point.
Certainly, as a ringed space, it is different from just spectrum of a field.
Yeah.
Yeah, but still, this criterion for local freeness does not work as stated. Yeah, well, in fact, it's not possible to state a similar criteria because somehow the underlying topological space is the same, but the ring space is more rich.
Okay, and can you please comment on the general form of the Riemann-Roch theorem? We just proved it for surfaces for invertible sheaves, but can we proceed using the same like induction maybe or something? And
no.
If not, what are the abstractions? So can we deal with?
First of all, you do well. You should not restrict yourself just to line bundles. You want to consider arbitrary rank vector bundles, higher rank vector bundles, and then you will have higher Chern classes. But the general form is that you can express the Euler characteristic of any vector bundle via the Chern class of this vector bundle. That's the general form.
The Euler characteristic involves cohomologies, yes, and
yes.
The definition. And
Yes.
Chern classes are defined using, I heard that something like draw rings or what?
For example, yeah, that's also some problem how to define Chern classes, not in topological setting, but in the algebraic setting. But you may think of some topological settings. So you may think that your base field is complex numbers, and so given a variety over complex numbers, you can view any algebraic vector bundle as a topological vector bundle. Then it has its topological Chern classes. There are elements of singular cohomology, and then you integrate those elements of singular cohomology against some so-called Todd genus. So it's like Hirzebruch formula for signature in terms of L genus or A genus, something like this.
I think we discussed it 2 years ago. Or,
right, absolutely, right, in the topology course, yes.
Okay, and
but
right,
the point is the miracle is that something absolutely algebraic, geometric, this Euler characteristic, is computable in terms of something absolutely topological, like Chern classes and their integrals over your variety. And this is miraculous because the Euler characteristic is something subtle. You need algebraic higher cohomology, and you compute it in terms of something very rough, just in terms of.
But once again, I understand that it works only on complex numbers, and like you, different fields involves
respell it, in algebraic terms, as you say, in terms of Chow groups. Yeah, it is possible to define Chern classes for algebraic variety. That's what Grothendieck did.
But then there is no miracle because algebraic stuff is expressible using different algebraic.
Okay. If you don't want miracles, no miracles. Okay.
Like cohomologies got replaced with Chow groups.
Yeah, but still, the Chern classes are rigid, so to say, and rough. But the
rough under what? So what is the roughness? So I understand that. Okay, topologically, so topological bundle.
If your variety and your vector bundle is deformed, then those guys do not deform at all.
Deform means
on the other hand, you can argue that if your family is flat, then the Euler characteristic does not deform either. So this equality has some chance to be true, and it is true.
Okay, and another question is about schemes. So I heard that schemes are great because you can study them on different extensions on your field, or you can reduce them.
For example, and also,
subfield.
Well, we will next week we'll start developing the Hilbert schemes, and the Hilbert schemes are some moduli. They are solutions of some moduli problems, so they somehow arise naturally in nature. But those Hilbert schemes necessarily, usually they necessarily have nilpotence, so that they are not varieties. You formulate some very natural problem, say, for varieties, but its solution takes you out of the world of varieties.
So the object that represents some certain functor is not a variety.
Yes, they are not varieties. They're only schemes. Well, in some very particular, special, and lucky situations, they are varieties, like point schemes on surfaces, for example. But even if you can already consider point schemes on three-dimensional varieties, then they will have nilpotence.
Okay, I see. But looks like this is something crucial that allows us to take points of your scheme on different subfields on your field. So a variety was defined.
Yeah, this is also very important. This example we'll consider next Tuesday for counting points over curves over finite fields. So it'll be very, very important to consider, well, if you want varieties, but not over algebraically closed field. This is also very important. But also many schemes are more general than that. They have nilpotence.
Okay, thank you.
Welcome.
I think there is a... Короче, вот мы не определили вроде как морфизм схем. То есть если в алгебраических многообразиях было все понятно, это просто непрерывные отображения, которые сохраняет регулярные функции, то тут как бы не очень понятно.
For morphisms, just no problems, because schemes are ringed spaces, and you must have morphisms of ringed spaces that are locally arise from morphism of rings. So you see, your schemes are locally like spectra, and the maps between spectra they arise from morphisms between rings, and they're the same for schemes.
Но просто когда мы определяли вот эти окольцованные пространства, у нас по определению там были кольца функций.
Yes, and now it's more fancy, but still you just need morphisms of ring spaces, nothing else.
Ну, хорошо, понятно. Спасибо.
А вот можно вопрос про кольца функций?
Yes.
Например, рассмотрим А1, но не над полем, а над кольцом там Z, например. Тогда что вот тогда вы говорите, что здесь не нужно думать про то, что структурный пучок выдает функции на открытом множестве.
Yes, certainly. Say
Почему?
for spectrum of integer. Yeah, you can consider spectrum of integers. Then
Spectrum of
just of integers.
A1.
No, not necessarily. You may consider A1, but you may just consider the ring Z itself and take its spectrum.
Yes, okay.
Already here the problem will be visible. Yes, and what's the question?
Z is not a function. Is not.
Yes. So the points are the generic point that corresponds to the zero ideal, and in its closure you have all the other points, and all the other points are just prime numbers: 2, 3, 5, 7, and so on, right? So a function takes different values at different points. So at point 2, for example, it goes to well, its value is a rational number that has no powers of 2 in denominator. At 3, the value is a rational number that has no powers of 3 in denominator, and so on. In case the functions go just to numbers, because those localizations numbers. That's because you're in but if you have divisors, you will not be able to say this way. Then there will be absolutely nothing in common. But in your ring is integral, all the localizations are contained in the same fraction field. And in this sense, you can say that the functions that take value in this fraction field, but somehow that's not quite what you would like to imagine, because you'd rather like to imagine that the values of our function at 2 lie in F2, at 3 in F3, at 5 in F5, and so on. So they are like the residues.
Yes, okay. And the question on generic point.
Yes.
Generic point is always unique. Yes, it is always a zero ideal.
Well, I don't know. It depends on your whatever terminology. If your well, underlying variety has a few irreducible components, then each one of them will have its own generic point. You may say it like that.
But
like if you take coordinate cross, so the ring is polynomials in xy modulo x times y, then there will be 2 generic points. One generic point will be rational functions in x, another one rational functions in y. Yeah.
And once again, I have a question about the general form of the Riemann-Roch theorem. Could you please just illustrate its power, except for one miracle that happens? What's more? How can we? What?
How is it formulated in general, or what?
No, not the formulation, but some corollaries maybe that we can use for general.
From Riemann-Roch?
Yeah.
Well, I don't know. There are innumerable. Somehow, unfortunately, the life is short. So if we continued next year, for example, we could study surfaces in more details. Like, I don't know, you must have heard that a cubic surface in P3 contains 27 lines. And certainly in the process of proving this, you need the Riemann-Roch theorem. In fact, for any computation at all, you need the Riemann-Roch theorem. So it's one of the most basic theorems in the world. So like for curves, you see, for curves, you use Riemann-Roch everywhere, always. The same in higher dimension.
Okay. So just like the basic theorem of algebra, arithmetic.
Yeah, absolutely. Yeah, absolutely.
Okay.
Okay, so let me save the notes. And
can I ask now
yes.
on what is called Jacobian? It is the same what we had in our homework. Is it the same as the Picard variety?
It's only 0 degree Picard variety, right?
Jacobian is a 0 degree.
Yes.
Okay.
Zero is Jacobian. Yeah.
And it is the variety which represents some functor. It is defined as
absolutely, yes. Yeah.
Universally, functorially. Yes.
Yeah. But somehow we'll not go into this. It is the next thing after Hilbert schemes. But I do not plan to go over Picard varieties in general, or Picard schemes in general.
You do not plan to do it this year?
Yeah, or maybe this life. Yeah.
This is the reason why we need Picard schemes. Why we need Picard schemes, not just Picard variety?
Well, again, in general, for curves, for example, Picard schemes are smooth and they're just Picard varieties. But in more general situations, say for surfaces already, or for some non-smooth curves, those Picard things will be, the Picard functors will be representable, but not by varieties, but by schemes in general.
Oh, yes. Thanks.
Welcome. Okay, so if there are no more questions, let me stop the recording and say goodbye to everybody. And next time we'll meet, well, some of us will meet at the math department.